Bob Budnitz. I'm sitting in my home office in Berkeley, where we've lived for more than half a century. And this lecture is going to talk about a technological revolution. I'll explain that in a minute. But first, I want to explain what I do. I'm a nuclear engineer. I was trained as an experimental physicist, but I'm a nuclear engineer. And what nuclear engineers do is we design nuclear power plants, or we analyze them, or we understand how they operate, or we improve their safety, or in some cases, some nuclear engineers actually help to build them. I've done most of my work over all this time analyzing them. And what analyzing them means, you have a nuclear power plant that's running, or maybe it's in the design stage. An analysis is necessary in order to understand everything you need to know about what might cause an accident. Just the same way you might analyze an aircraft to understand all the things that could go wrong, that could cause an accident. And then you want to make sure that there's a system in place so that that accident can't happen. Or if it does happen in a nuclear power plant, that the consequences are very low rather than very large, because a really big accident is a terrible event, as I know you know. So what I do is I've been doing nuclear engineering all this time. Most of it, I was at the Lawrence Berkeley lab for a while, but most of it I did as a one-man consultant. I had a one-man consultancy in Berkeley for a quarter century. And then at the end of my career, I went back to the Lawrence Laboratory again for briefly, and then I retired, and now I have a one-man consultancy again. And it's a pleasure. I'm a UC retiree. It's a pleasure to be able to give this talk, and I'm going to tell you what I'm going to explain today. I'm going to talk about a technological revolution that's underway right now in the field of nuclear safety, nuclear engineering, nuclear power. And I'm going to explain why this revolution is wonderful, but also why it's needed. And then I'm going to explain the issues that stand in its way, because there are a whole lot of things that stand in the way of this technological revolution actually becoming realized. So, but before I start, I'm going to tell you what I mean by a potential technological revolution. It's easy to explain. I'm old enough so that when I was a kid, if you flew from San Francisco to the East Coast, you flew on an old propeller plane. I was in college when the jets came in. The first jet aircraft came in the late 1950s. And the old ones were, all of a sudden there were 707s and the DC-8s. And if you don't understand, I'll explain what I mean by a technological revolution. That was an absolutely fantastic technological revolution. It had huge economic benefits. It had huge convenience benefits, but crucially, it had huge safety benefits. The new jets, and then since then, are so much safer than those old propeller planes that I flew in when I was in high school and college, that you couldn't believe that we would still be flying those old planes now. Just to describe, when I was in high school and college, there were crashes. The aircraft, the traffic was 1/10 or even less than what we have now, but there were crashes, big crashes, several times a year. In the first 10 years after that advent of those jets, the probability of a passenger being killed in an accident dropped by a factor of 10. So that when you got on a plane, you had 1/10 the probability you had before. In the intervening 40 or 50 years, since that first 10 years, it's dropped by another factor of 4 or 5 additional. So that today, when you climb on a plane, the probability is only 2 or a little more than 2% as high as it was then, that you would that you're going to die in a crash. It's a huge safety technological revolution. Now, of course, we just had a crash the other day. It's very rare. You know how rare it is. Heck, when I was in high school, husband and wife flying to California with little kids would fly on separate planes. One would fly in the morning, one would fly in the afternoon, because they're afraid a crash would kill them both. Nobody does that anymore. We don't have that fear anymore. That was a revolution, and it was technological in its origin and in its implementation. And what I'm going to tell you today is about a potential new technological revolution of comparable importance in the field of nuclear reactor power. Nuclear reactors make electricity. They also do some other things, but they mostly make electricity. And they've been around for a long time. And I'm going to explain why this revolution is both upon us and why it's necessary. But first, I'm going to tell you a status about the current status. Today, in the United States, nuclear power, we have about 90 odd reactors on about 60 sites, almost 100 reactors on 60 sites. And it generates more or less 20% of the electric power in the United States, 20%. Worldwide, there are over 450 reactors on about 250 sites. I'm not sure the number. And it generates about 10% of all the electricity in the world. 20% in the US, 10% worldwide. But, and this is an important but, most of those 400 and odd reactors that are running around the world are older. Most of them are older than 20 or 25 or 30 years old. And in the United States, most of them are older than 40 years old. Almost no large new reactors have been built worldwide. A few have been built. China's building them, for example, and a few here and there. But almost no new reactors have been built around the world in the last 10 or 20 years, although the 400 odd that are running continue to run, and they run well. Now, all of those reactors, almost all of them, that are running around the world are very large. The typical size is more or less 1,000 megawatts. And if you don't know what that is, I'm about to explain. Each 1,000 megawatt plant in the United States produces electricity for about 750,000 people and a proportional amount of all the commerce and industry that we have in the country. As I said, in the US, it's about 20%. So each one of those big reactors can support, 750,000 people. There are often two on a site, like in California here, we have two, PG&E runs two of them at Diablo Canyon and halfway down the coast from here it's near San Luis Obispo. And there are typically two on a site, sometimes one on a site. A few of them have three. And they have the following important features. Those plants are base load plants in the sense that they run 24 hours a day, 7 days a week, with a typical availability and reliability of over 90%. They go down every 12 or 18 months for a few weeks to refuel, and the rest of the time they more or less run all the time. So it's a terrific base load source of electricity that is highly reliable. And by the way, during the 18 months when they run between refuelings, every so often it'll go down for a day or two, or sometimes even a little longer for some problem. But most of the time they're just running all the time, and that's the feature that's very important about it. Now let me explain where they are. It's easy just to talk about where they are. Of the 450 of them, about 30% of them are in the US and Canada. About 30% of them are in Europe. About 30% of them are in Asia, China, Japan, Korea, Taiwan, a few of them in India, but mostly China, Japan, Korea, and Taiwan. And about 10% of them are in Russia and Ukraine. They were built in the Soviet times when it was Soviet, but now it's Russia and Ukraine. So it's 30% US, Canada, 30% Europe, 30% Asia, and 10% in Russia and Ukraine. And that's where they are. There are a few here and there. There are a couple of sites in Argentina, and there's a site in Brazil and in Mexico, but they're here and there. But the rest of them, that's where they are. Now, of these very large reactors, about 1,000 megawatts, about 50 or 60 of them, I'm not sure what the count is now, are under construction now, but most of those are under construction in China, or the Russians are building them. And the reason why they're not under construction everywhere else is because today they're hopelessly not economical to build and make electricity. I'll explain that in a minute. To build a new one today is hopelessly not economical. And as I said, I'll explain that later. Let me describe how the regulation of these reactors works. Every country that has a reactor has an agency. In the United States, it's called the U.S. Nuclear Regulatory Commission that has regulations, and they regulate the reactors. You have to get a license from them. The British have one, and the French, and the Russians, and the Chinese, and the Japanese. Everybody has their own agency, and those authorities license these reactors. And if the new ones come along that I'm going to talk about, they're going to have to license them too. But today, the regulations around the world are all different one to the next. And that means that selling them worldwide is a nightmare. That is, if General Electric is trying to sell a reactor in the US and they get a license, They can't take that license to the UK, never minding to China or or Spain, because they have to get a different license with different requirements. And that system, which is going to be changed in the next few years, I'm going to tell you about that later, is an important impediment to very broad expansion of nuclear power. A couple of other things I want to talk about today's situation, and then I'm going to talk about the future. Today, every time something goes wrong in any nuclear power plant in the world, a pump fails in Spain, or an electrical system fails in California, or a turbine fails in India or wherever it happens to be. Every time a failure like that occurs, it is written up by the people that experience it. They explain what happened, explain what they think the problem is, and they publish that, and it's published and learned about worldwide. So that if this pump fails in Spain and you've got one in Argentina, you'd say, oh, I'm going to learn from that and figure out how to fix it and make it better. And that every reactor in the world shares that data. And that sharing has helped make the reactors much safer and more reliable. And the reason is if something goes wrong, everybody gets to learn about it and fix it. And that is a really, really important part of the international regime today, the sharing of data, which everybody does. Now, what that has led to is that the safety is way better than it was 10 years ago, never minding way better than it was 30 years ago. And we have a lot of indicators for why that is. Let me try to explain just one important indicator. You see, the way an accident happens typically is that a piece of equipment fails, and there's a backup, and maybe the backup fails too, and it causes something else to happen. That's a typical scenario that could lead to an accident. You have a failure, something else happens. So every nuclear power plant in the world is equipped with the following feature. There are, in the US, for example, a typical reactor, there are 25 or 30 or 35 different indicators of conditions. And if any one of those on the list has an off-normal condition, you've got to shut it down and fix it before you start it up again. You got to shut it down. And everybody does. And then you fix it, you write it up, and you go on after you're assured that you've got it back. Now they have both automatic shutdown systems, and then the operators shut it down if the automatic system doesn't work. Now, here's one way that we know that the reactors are safer than they were. In the year 1978, which is 45 years ago, and that was just before the accident at 3 Mile Island, we were running almost the same 100 reactors. But on average, a typical reactor in those days would shut down about 10 times a year, on average. Some a little more, some a little less, on average. About once a month, they would shut down. So that in the United States in that year, this is the year before 3 Mile Island, we have data, there were about 1,000 shutdowns for one or another off normal conditions, and then they would fix it and go on. And then we started all around the world to make equipment much more reliable. So that 10 years later, there weren't 1,000 shutdowns in the US, there were about 300. 10 years later, there were about 100. Last year in the US, we had about 3 dozen. Not 1,000 back then, 3 dozen. And if you look at the 3 dozen, most of them are little stuff, not important stuff, but nevertheless, you want to do it. So we know that the things that cause trouble are way less likely than they were before. And we also know, because of things we've done, that the operators are way better trained. And so the operator errors that might lead to a problem are way, way reduced compared to before. And that gives us confidence because we, people like me, analyze these accidents. We believe that the accidents that could cause trouble, they're not impossible, but they're way less likely than they were back then. Now, what makes the new reactors I'm going to talk about later better is that a lot of the problems we have with these reactors, if you started anew with a brand new design, you can design them out. So they not only are unlikely, you can make them impossible. Because some of that equipment, we don't even have that equipment. I'll talk about that later. So there are, nevertheless, and you all know this, two very controversial issues about the deployment of nuclear power around the world. Everybody understands this. The first is large accidents. Now, except for the Chernobyl accident, and despite people's fears, these accidents so far they have not killed a lot of people. I'm not going to poo-poo, we just lost 60 odd people in an airplane crash. You know perfectly well. You don't want to poo-poo that. But the Chernobyl accident in 1986 killed 30 odd people right away on the site. There were 180 workers that were treated and survived, and there were a couple hundred cancers that came off later. I'm not going to poo-poo that. That's a big accident. 31, I think, was the number of people killed on site just directly by that accident. 175 the workers were treated but survived, and a couple hundred cancers, and people died of that, and that's sort of the number. Now that's a big accident, but it's not a million, and it's not contaminating the whole country and so on. But there is a major issue, which is major land contamination, and that happened at Chernobyl in 1986 in the Ukraine. It certainly happened in Japan in Fukushima in 2011. Major land contamination is an issue, and we don't want to say anything about that except that the major point of trying to make these things as safe as they can be is to reduce the probability of that and reduce the consequences if it happens. And I'm going to talk about these new reactors in that context. And the second major controversial issue, I'm going to tell you this, you all know this, is radioactive waste. It's very, very toxic. It's highly radioactive. If you get near it, it's not good. But we have a technological solution for that that's been around for decades. It's to put it deep, deep underground in a place where it'll be sequestered and it won't be a problem. Now, this is not a technical issue. The US had a project in the desert in Nevada. It was called the Yucca Mountain Project 25 years ago, that did a design that was going to put all the radioactive waste in the US deep underground in Nevada. And an analysis was done and checked by everybody that could, that showed that waste was going to be sequestered and safe for 1 million years. The EPA and NRC requirement was 1 million years, and they showed it. And a lot of people reviewed it, and I reviewed it. I worked on that project for a while. And the total cost of that project, had it gone ahead, was a little more than 1% of the value of the electricity that was generated. It was not a big cost overall, deep underground. But that project was killed, as I'm sure you know, because people don't want it near them. It's a social, difficult problem about where to put this stuff, but it's not a technological barrier. Right now in Finland and in Sweden, they're proceeding with the first deep repositories like that they've approved and they're getting started on. And we're hoping that maybe we'll have an impasse broken here too. So I'm going to move on now to another topic, which is talk about the electricity in the US today, and then I'll come to my main topic. Today in the US, I mentioned that nuclear power generates about 20% of our electricity. Now, the next largest generator is coal. Today, it's just over 15%. I think it's 16%. But 15 years ago, it was 40%. Coal was 40%. Now it's down to 16%. What took up the slack? Natural gas. Today, natural gas is a little over 40% of the electricity. I said nuclear is 20, coal's 16, and the rest of it is renewables. Wind is about 10%, and solar is about 6%, and hydroelectric is about 6%. So altogether, nuclear is about 20% of the electricity in the US. Coal is 16% and dropping, and natural gas is increasing, and wind and solar are increasing. Now, besides that change in the mix of what's making electricity in the US, there's also a big change in our economy. What's going on in the last 5 or 10 years, and it's going to continue for the next 5 or 10 years at least, is a major change in the amount of electricity. The economy is becoming electrified in many different sectors, and I'm sure you know this. I mean, electric cars are 3 or 4% now. We even have electric 18-wheeler trucks, but that's going to be 10 or 20% in a decade or two, electric cars. We have the electrification of a lot of industry. Even ships are being electrified. And we have these huge data centers. You hear about them all the time. The internet data centers, and they're gobbling up electricity as fast as they can. And the amount of electricity that's going to be demanded in the U.S. economy, just as we are in 5 or 10 years or 15 years, is going to be significantly more. How are we going to accomplish that? Well, wind and solar are increasing their construction and share. Although I do want to tell you that about 2 weeks ago, the new president put an embargo on new wind on federal government support for new wind and solar. But I think that won't last very long because there's going to be a demand for it. So that's increasing, and that could fill that gap of needed electricity. Now, natural gas can fill the gap, but at the moment, right now in the US, there's essentially no new nuclear power being constructed. There's no nuclear at the moment. I'm going to explain why the revolution that's coming is going to change that. So what's going on is that if this electrification continues, it's either going to be more wind and solar, but I want to remind you that wind and solar, the wind doesn't blow all the time, like a third of the time, and the sun only shines less than half the time. You know that. And so you need base load, for the rest of the time, and it's probably going to be natural gas, of which we have plenty, unless nuclear power can come in and help bridge that gap. Now, let me explain the key thing that happened in the last 20 years. Natural gas today is much cheaper than it was 10 or 15 years ago. Like, it's about half as expensive as it was. And there's a huge supply because that was always there that we're now developing because of fracking. And so natural gas is a huge supply. It's much cheaper. And if nothing else happens, natural gas is going to be the fuel that's going to produce that electrification. But of course, natural gas produces greenhouse CO2, and that's not desirable. So it's going to be wind and solar or nuclear or something like that if we're going to solve all those problems together. So let's talk about the future. If I just talk about the future without any new nuclear power, I said to you, it's liable to be solar and wind and a whole lot of natural. That's not just in the US, but all around the world. Okay. But what's new in the nuclear power business, and that's going to be the rest of this talk, is this revolution I'm talking about. So let me provide the background for that. As I said, before a few of them shut, we had a little over 100 nuclear units in the US, like 103 or 105. And some of them have been shut. So we're down to 95 or 96 nuclear reactors in the US, the ones I talked about. And almost all of them are 40 years old or older. Some of them are only 30 years older. There have been 2 new ones, just 2, that's all. They're in Georgia. They're the only 2 new ones in a long while. But no new ones are being built. Now, let me describe something about the acceptability of this. About 15 years ago, when this increase in electricity was apparent and the utilities were trying to figure out what to do, the electric utilities in the US placed about 30 orders for new reactors. This is about 15 years ago. 30 orders from companies like General Electric and Westinghouse, and some were from the French, and they were going to buy them from Japan, so on. And then within 5 years, almost all of them were canceled. Only 2 were built in Georgia, and they're running now, and the rest were canceled. Why were they canceled? Because in that short period, they didn't anticipate cheap natural gas. It led to the cancellations, and natural gas came in and it took up the slack, and all of those plants, but 2 of them were canceled. And today, except in places like China and Russia and a few others that have planned economies, there's no new large nuclear power plants, really hardly any, being built anywhere in the world because they're too expensive. They can't compete with the other ways of making electricity. And by the way, the Chinese are building them, but their economics is very obscure. And same thing with Russia. You can't figure out what those things really cost because of these odd economic subsidies that are buried in and hidden in the way they figure out what things cost over there. But except for places like that where the government does subsidies, there are very hardly any new nuclear plants being built anywhere. So let me talk about, were they being built or new ones are going to be built? Who pays for them? Well, there are 2 ways. We, like PG&E in California, we have large electric companies that are regulated, And the rates that they can charge are in the rate base, and you pay your PG&E bill every month or your whatever electricity you have. Based on that, it's a government-improved guaranteed rate of return to those electric utilities. There are a few plants in the U.S. that are not regulated like that. They're owned by a company that has to make a profit, and they either make a profit by selling the electricity or they don't make a profit. Around the world, a vast majority of the nuclear power plants elsewhere in the world are not owned by companies, but they're owned by government ministries. For example, just the example in Russia, it's a government ministry, and they're running the few dozen reactors, electric ministry, and that's the way. And they're the ones that would build it in those countries, and in countries like ours, it's going to be these companies. But it is my prediction that, and I think everybody in the business that I'm in will agree with me, that without a revolution, nuclear power plants are not going to have any future, or not an important future anytime soon. And it's because of the economics. Now, there's one important thing I need to say, and I won't ever mention it again, and that is there is no problem with the fuel. We have enough uranium at acceptably low prices for centuries of running whatever we want. There's just no problem with uranium. There's plenty of uranium. Anybody tells you that, that's just not right. We've got a lot of it. It's not expensive. If today a typical nuclear power plant that runs makes electricity, only a couple % of the value of electricity is the cost of the uranium. Not very much. And so, what if it doubled? It become 4%. It's just not. There's no problem with uranium, and I won't touch on that again unless you ask me. I'm happy to. Let me go on. Now, here's the revolution, and I'm going to talk about it next. The revolution is that over the last 10 or 15 years, a whole lot of advances in technical capability and technology have made feasible the use of much smaller reactors. We call them small reactors or small modular reactors. I'll explain what modular means in a minute. That are now feasible to make without having a diseconomy of scale the way they were before. The big reactors are big because in those days, it was much cheaper to build a big 1,000 megawatt reactor than to build 10 100 megawatt reactors, because you had to build the components and you transfer to the site, and manufacturing was inefficient and so on. But today, because of advances in automation and in manufacturing and a whole lot of other things, it is now, by the companies that are doing this believe it, it is now believed to be more efficient and more cost effective to make small reactors that you make in a factory, and then you transport the whole thing on a railroad car to the site. And instead of having 1,000 megawatts, you might have 10 100 megawatt reactors or 5 200 megawatt reactors. So that at Diablo Canyon, which has 1,200, that's in San Luis Obispo, California, and at 1,200 megawatts times 2 is 2,400. Instead of having 2 reactors for 2,400 megawatts, you might have 12 200 megawatt reactors, all identical, transported to the site. That's the scheme. And that is made possible by advances in manufacturing and the idea that if you have a factory that is turning things out in numbers, you'll get economies of multiple, the way Henry Ford did with cars, with the assembly line tactics and so on. And you get better quality and the like. And so this idea took off about 10 or 15 years ago. Right now, there are worldwide over 50 development projects underway in many different countries. Large companies like General Electric and Westinghouse and Toshiba and Mitsubishi and the Russians and the French and the Koreans and in China and so on, in Britain, very large companies, and some of them are smaller companies that, Bill Gates has a company that's doing this, one tiny little company. It's nothing like GE, but they're small venture capital companies. And some of them are being designed by government institutes like our big national labs, but elsewhere, around the world. And there are over 50 of those SMR, small modular reactor projects, being developed. The first of these small reactors were deployed in Russia just a couple of years ago. And there's a half a dozen more being built in China, and there's actually one in Argentina, Russians and so on. There are a dozen new starts getting going. I'll talk about those later. And the hope is that these new technologies, some of them, all 50 plus companies and institutes can't sell them, but the ones that went out will, that they will become the hope for the future and that nuclear power will expand in this mode. Now, another thing that's important is that in this mode, it can expand to many other countries that don't now have nuclear power, and I'll talk about that later. Now, let me explain why these small modular reactors make sense. I mentioned factory fabrication, and then you can put it on a train to the site. And the manufacturing is not only clever because of that, and robotics and so on, but there's less labor in the manufacturing, and the modularity makes them similar. And by the way, factory labor is very different in its skills and in its error rate and so on than construction crafts out at a site. It can be made quicker, shorter time from when you place the order to when you get the thing going. It could be 4 or 5 years instead of 8 or 9 years. And crucially, the capital requirements are smaller per module. Instead of having to spend $6 billion on a big one, you can spend 610 times. And that turns out to be way easier to finance for these ministries and companies. So the capital requirements are not only less, but they can be less per module because of the idea. And so the whole idea of this, which is still to be played out, is that they're supposed to be, the promise is that they're going to be cheaper. And by the way, with smaller units like that, it's much better for a weaker grid. There are countries in Latin America and in Africa and places like that don't have a very strong grid. And if you have one great big 1,000-megawatt unit drops off, it can cause a huge perturbation in the grid. But if you have 10 little ones and one of them drops off, it's not such a big perturbation. It's much better for the weak grids in those countries, in those places. So there are advantages to these small units that are transparent. Now, the other major advantage, and I'll talk about that in a minute, is the safety advantages. They are transparently safer. I'll explain. But before I explain the safety, I have to explain how they work. The way it works is no matter what technology you use with a reactor, the chain reaction ultimately generates heat. The radioactivity that's created generates heat. I haven't got the time to go into that, but it generates heat. And in most of our reactors today, that heat boils water or makes water hot. And then the steam drives a turbine, makes electricity. In some of the reactors, you actually make a very hot gas and it drives a gas turbine. And that heat then makes electricity, or you can use the heat for industrial processes too. But the safety problem with these reactors is that there's a hell of a lot of heat. And unless you can remove that heat safely, the thing it's an accident, the thing will heat up. And you know about this perhaps. It would heat up, the fuel will melt and releases radioactivity, and you got a great big accident. So the key to making these things safe is to make sure that you have heat removal that's very highly reliable so that you won't get those accidents through disruption. Well, what causes accidents? There are two things: either equipment that is unreliable and breaks, and I mentioned that that's still possible, but it's way less than before, or an operator can make a mistake. So what's new about these clever new designs? Two things. Well, really three, but two. They're designed with much more reliable and smaller components than the previous generation, because we've learned a heck of a lot about how to design really reliable smaller components than the great big components that are in the other ones. And the second is they're designed with almost no operator intervention for months at a time. It's like the autopilot on you take off from San Francisco, it's autopilot all the way to New York until they land. The operator, that's the pilot, doesn't have to do much. The current reactors have a whole lot of operator intervention that's necessary, and they can make errors, or they can even they can make errors of commission, or they can make errors of omission. These new designs are designed specifically to have very little operator intervention that's necessary. That should make them much more safe, and we're confident about that. And then the third thing that's different is that these new reactor designs almost all take advantage of terrific advances in materials science. There are materials, metal materials, ceramic materials, various kinds of materials that are way better than the materials we used before. both for the fuel and for the containers and all for the equipment, that make them much less susceptible to failure and make them much forgiving if they do fail. And then finally, because these reactors are smaller, if they're only 1/5 the size, there's way less radioactivity and less heat. It's easier to manage, and the consequences are less. Okay? So altogether, if you do an analysis of these reactors, it is confidently understood by everybody in the community, and I'm one of them, that they're going to be way safer than before. Okay? They're going to be easier to operate. They're going to be, we hope, less expensive. We don't know. But the main barrier is the cost. We don't know yet whether the cost of building these things is going to be low enough in this mode of build a factory and factory fabrication. Well, if I was giving this talk 6 months ago, I would have told you the following, that what's going on 6 months ago, and it was true, and it's still true, is there are at least a dozen or maybe even 15 orders out there where an electric company overseas and so on have ordered one of these units from one of those manufacturers. They ordered one. And the hope was over the next 3 or 4 years, they'll build one, and then it'll be great. And then, and then they'll order 10. But the first one in that scenario is not going to be cost effective because it's way more expensive to build the first one than it is to build multiples in a sort of assembly line. And you understand that. Everybody does. Even though the government is helping to overcome some of those barriers with assistance and that sort of thing. But something has happened to that barrier in the last 3 months that has changed things dramatically. I'll just give an example. Google has signed a contract with one of these small vendors. It's all contingent on they have to get a license, from the government, in which they're going to order 10 of them. And if that goes through, that company is going to be able to put together an assembly line to build 10, rather than the old scenario where they're going to order one and then build it, and 5 years later we're going to wait and see. Okay? After that, Meta, which is Facebook, is talking about ordering 10 of them. They want to use them for the data centers. That sort of thing. And Amazon has also, it's been in the press, talking about it, signing a contract with yet again another one of these, in which they're going to overcome this problem of having to build one and wait 5 years and see if it works. They're going to bet on the come, and of course, they have to get a license from the Nuclear Regulatory Commission, and I'm coming to that next. And that could jumpstart this whole process. Of course, the ones that don't make such sales will have to fall by the wayside because there are 50 of them around the world, more than 50. But the hope is that we're going to finally see a few of these getting going in the next few years, and that the economics will work out. There are still some important barriers. The rest of the talk is going to talk about that just in the next few minutes. The most important barrier is safety regulation. I mentioned before, today, every country has its own regulatory agency, the Nuclear Regulatory Commission. By the way, it's like the FAA. They have regulations, and they inspect, and they'll fine you or shut you down if they need to, and they fix, they do that. But you know perfectly well that the FAA regulates, let's say, Boeing. And if the FAA says that the Boeing is fine, that's accepted all around the world. Boeing doesn't have to get a separate license from every country that they land the plane in. That would be 100 countries. That's crazy. But the way it is in reactors is every country has its own agency today, and all the regulations are different. So it has been recognized for the last several years that we need one set of regulations that everybody agrees to worldwide, and everybody will use it. And then if you get a license in the UK, you can build that reactor in Canada or in Australia or in Spain or in Romania. So the idea of having one set of regulations, and then you meet it and you can demonstrate it and then sell it around, that's now underway. The several countries around the world are now working together to develop an advanced set of regulations that will be similar all around the world. And then when some sort of certification occurs, it can be used internationally. And then General Electric can get a certification here, and they can sell it in all those countries. And by the way, Toshiba can get a certification in Japan, and they can sell it all. You understand the benefit of that. Well, that turns out to be in the mix of international politics, and despite all the difficulties that we're having with the Russians and all that stuff, It turns out that everybody's cooperating on this together because it's in everybody's interest. And it's being done partially coordinated by the UN's agency in Vienna called the International Atomic Energy Agency, IAEA. And there's been major progress in the last 2 years. I mean, one example of right close to home is our NRC and the Canadian counterpart are working directly together on regulations that will help the two do it together. And the reason that's important is easy to explain. General Electric has sold their first two of these in Canada. Okay. And so if the Canadians approve it and then we have it here, vice versa, just think about how important that is compared to if it weren't true. So we're hoping that that regulatory coordination will occur. And it is, and it's underway. And we're hoping that in any event, that shouldn't be a barrier. But I have a couple other things to talk about, and then, of course, I'll ask for questions. First, there are a couple of things I want to tell you about that are not a barrier. We got plenty of companies that will manufacture and design these things. I told you there are over 50 of those designs around. Many of them are going to have to fall by the wayside, but they're going to be there to help support this big international industry. And the second thing is, this is something that was not true 10 or 15 years ago. Today, there are plenty of trained nuclear engineers and plenty of people in the pipeline. Our nuclear engineering departments here and overseas are overrun by applicants. That wasn't true 15 and 20 years ago. Today, you can go to any department, we have one at Cal, and their applicants are overrun, and the best ones are coming in, and it's really a marvelous difference. There doesn't seem to be any shortage there, and we're hoping that that'll continue. And there are plenty of companies to support this. I just have a couple other things to say, and then I'll talk about questions. I want to talk for a minute about newcomer countries, that is, countries that have never done this before. Now, some of the newcomer countries are pretty advanced. I mean, the Norwegians never had anything, and if they go over, that's an advanced country. But I don't have to tell you, because I don't want to name names, but there are some countries that have a terrible political culture and a terrible safety culture. Bribery is endemic. You know, there are some countries that are today the way the Soviets were at that time, top down. If somebody down below finds a problem, they have to bite their tongue, because if they complain about it, they not only won't have the problem fixed, but they're liable to lose their job. That's what happened in Chernobyl. Somebody knew that accident was coming, and they were afraid to tell for fear that they'd be sent to Siberia. And so it went ahead, even though they could have stopped it, because the culture was top down and they were afraid to crisscross their managers. Well, there are places today like that. And if you have a culture of corruption, if you have a politicized culture in which a regulatory agency is weak and it's not independent and so on, then you really have an issue in which these reactors aren't going to be as safe as they need to be. Okay, and that's and there's also a political culture in some of these countries. I'm not talking about the U.S., but we're talking about a political culture in some of these countries in which you imagine that some politician appoints a regulator and somebody squeals on him, and that person, you know, they can send the equivalent of sending him to Siberia. So we need to emphasize that, and that's understood worldwide. And there's a major push all around the world to make sure, and people are working on this hard, that when they sell a reactor in one of those countries, that this attitude doesn't occur at the reactor, even if the corruption is everywhere else. You know, there are countries where you can't get a contract to pave a street without paying a bribe. We all know that. And the other thing is that in some of these countries, they may not have the capital, some of the smaller countries or weaker ones. So there's now, in several of these schemes, the country that's selling it is going to finance the economics with a 10 or 20-year loan so that the reactor can be built in a country in, let's say, in Africa or in Latin America, a poor country. And that huge effort to bring about a change in culture is underway. It's widely recognized, even in the places where people recognize there's a problem like that. And the expectation is that the companies that are selling these won't sell it in a country like that. If there's going to be bribery, that's a problem. Okay. One last thing, and then I'm off. I talked about radioactive waste storage, but the thing I want to talk about is the linkage to proliferation of nuclear weapons. It's easy to explain. Every reactor that fissions uranium makes a little bit of plutonium in the reactor core. It's because the neutrons get captured on the U-238 and they make plutonium-239, and it's a fissionable, it's what the bombs are made out of. And if you could get a hold of that used fuel and do chemical reprocessing, you can extract plutonium and make a nuclear weapon out of it. That's called proliferation. And that's been a concern for 50 years or even 60 years. Now, the big concern always was with governments, because governments can do that. In fact, that's the way a government can do that. But it doesn't seem like it's a concern for terrorists getting a hold of that stuff. And the reason, unless the terrorists are like a government, because it's a huge technical endeavor that takes years and years and years. But it remains a concern. So the thing that's going on now that's important is that internationally, the companies that are going to be selling these things are going to be internationally taking great care to make sure that that proliferation with concern is dealt with the governments before they sell a reactor in country number 3 or country number 33. Okay, I'm not sure that that can be addressed perfectly, because that's always a danger. But these reactors look like, the new ones look like they're very hard to do that reprocessing anyway, and it looks like it's probably not the right approach anyway. If a country wants to proliferate nuclear weapons, they probably wouldn't even today do it by taking reactor fuel. They're going to do it by taking uranium out of the mine and enriching it in those centrifuges, the way it's going on in Iran. And that hasn't to do with reactors at all. That's just plain enriching uranium to make weapons. But it hasn't to do with reactors. So that although the plutonium proliferation concern is there, and I'm not going to poo-poo it, it's probably not going to stand in the way of a widespread adoption of these small modular reactors. We don't know. So let me describe the wrap-up of this, and I'm happy to take questions. What we don't know yet is whether enough of these reactors that have been designed will be sold and will be manufactured, and in the end will be economical. If Google and the first 10 are economical, that'll take off. And if they aren't, well, they won't. But the technology that Google's ordering is very different than the technology that Facebook is ordering. One of them is a molten salt cooled reactor, and another one is a liquid sodium reactor, and then another one is a water cooled reactor. The technologies are different. So one of them might turn out to work out. I'm talking about economics, and another one might not. We don't know. There isn't anybody in the world who can tell you that. We just don't know. And we're not going to know for a while. But it's going very fast. And the revolution is now going so fast that there are places that said where they were standing on the countries, for example, that were standing on the sidelines are now wanting to jump in and get in the queue, lest they lose 10 years while somebody else is in front of them. And I'm watching this every day over the last 6 months, and it's exciting, but it's also very, very uncertain. Will this revolution occur? I expect so. Is it going to happen in my lifetime? Well, I'll tell you, I'm 84, okay? If I live to be 100, maybe. How's that? I mean, I'm being sort of modest about this. I don't know. Nobody knows. But the technical rationale makes sense. And the economics is beyond me to understand. So thanks a lot. I'm done with it, and I'm happy to take whatever questions you might have.
Thanks a lot, Bob. That was a great talk, and it's